For section A1, we focus on hydrostatics and buoyancy force. My first question is in reference to the in-class example done on August 26th with a dam setup. How does atmospheric pressure affect the hydrostatic pressure shown in the image of a dam system below? Does the function of the pressure's growth change, and how does the atmospheric pressure affect the total pressure volume? The increase in pressure is simple as the depth increases remains linear. However, the atmospheric pressure adds a constant value, and it increases the total pressure by the atmospheric pressure value times the height of the dam. In my second question, which is the calculation question, a perfectly cylindrical buoy is submerged underwater 5 meters beneath the surface with a radius of 2.5 meters. The buoy has remained at the submerged depth for a prolonged amount of time. What would be the density of the buoy if the buoy is 20 meters tall? Below is an image, and this is based off of the floating block problem demonstrated in the videos. And in the answer, we use the KFAPS method, which is known, find, assume, plan, and solve. For the knowns, we know the gravity is 9.81 meters per second squared, the radius is 2.5 meters, the height of the buoy is 20 meters, the depth submerged is 5 meters, the cross-sectional area of a cylinder is pi r squared, and the density of water is 1.00 grams per meter cubed. And what we're trying to find is the density of a buoy submerged at 5 meters. We can assume that the buoyant force is equal to the weight of the fluid displaced because the buoy is at equilibrium with the water and that the water is pure. The plan for this is to solve for the cross-sectional area of the buoy, use Archimedes' law, and solve for the density of the buoy using Archimedes' law. So below is the solution to where the cross-sectional area comes out to pi times 2.5 meters squared, which comes out to 19.6 meters squared cross-sectional area. Archimedes' law is the density of water times the cross-sectional area of the buoy times the depth submerged times gravity, and it's equivalent to the density of the buoy times the cross-sectional area of the buoy times the height of the buoy times gravity. Then the density of the buoy can be simplified out and reversed and moved and arranged in a way to where it is equivalent to just the density of water times the depth submerged over the height of the buoy due to the cross-sectional area crossing out and the gravity crossing out. We get 1 gram per meter cubed times 5 meters over 20 meters, which equates to 0.25 grams per meter cubed for the density of the buoy.